Now I'm going to talk about compactness and subspaces. So firstly, let X be a compact space and Y a closed subspace. So in other words, a closed set with a subspace topology. So then Y I'm claiming is also compact. Okay, so any proof of compactness basically has to start like this. So we have to say let VI, I and I be an open cover of Y. Okay? And so somehow we have to come up with a finite subcover. And basically the only way we can do that is somehow by relating it to the assumption that X is compact. So somehow we have to come up with an open cover of X and take a finite subcover of that. So first thing to say is to remember what it means to say that these VIs are open. So remember, this is how we defined the subspace topology. So a subset of the of Y is going to be open if and only if it's the intersection of intersection with Y of some set that's open in X. So that means we can choose these sets UI. Okay, so now you can say, well, yeah, we wanted to have an open cover of X so that we can use the compactness of X. So is it true that these sets UI that they cover X? Well, no, it isn't. We know that the UIs will cover Y, but Y might only be a tiny part of X, and we haven't said anything about covering anything else. But we've got this other assumption that we need to use somewhere, that Y is a closed subset. So that's the same as saying that X less Y is open. So I'm going to claim so if I take these this family of UIs and then I also throw in the complement of Y, I want to claim that's an open cover of X. Well, certainly all the sets involved are open, right? The UIs we chose to be open, and like I say, Y was assumed to be closed, so X less Y is open. We've got so we need to check. So suppose X is some element of X. We need to show that it's in one of the sets of this family. And so first possibility of X is not in Y, in which case it's in the complement of Y. So that's one of the sets in the family. Okay, then if X is in Y, well then by assumption, these sets VI they cover Y, so we can choose some I such that X lies in VI. But that means then that X lies in UI, right? Because VI is a subset of UI. Okay, so now we've got an open cover of X, so there must exist a finite subcover. So that means that we can choose some finite set Okay, so we've got a we were looking at this family which contained all the ui's together with the complement of y, and so we've got some finite subcover of that, which might or might not contain x less y, but if it doesn't contain x less y, then we can just throw that in. It doesn't make any difference. So we might as well assume that this finite subcover involves x less y together with some finite number of the uj's. Now, if y is in y, then okay, so y is in y, well, in particular, that's y means y is in x, and so y lies in one of these sets. Okay, it lies one of these sets in this family here. But of course it can't lie in x less y, because it lies in y, and so it can't be in the complement of y. Therefore, so it lies in some uj. Oh yeah, and then we have to say then okay, so it lies in some uj, but also it lies in capital Y, and vj was the same. We chose vj such that vj is uj intersect y, so we're lying in uj intersect y. That's equal to vj. Okay, so that means that these sets Vj, for j just in this finite set capital J, they still, that's a subset of the original family of VIs, and it still covers the whole of the set Y. So that's our required finite subcover. That's what we needed to produce in order to show that Y is compact. So we just had a theorem saying that closed subspaces are compact in the case where the total space is compact. Now we want a theorem in the opposite direction, saying that compact spaces are closed. And but in this case, the appropriate assumption is that the total space should be Hausdorff. So we've got a Hausdorff space. Okay, so it's Y is a subspace, and we're going to assume that if we give Y the subspace topology, then it becomes compact. Then I want to claim that Y is closed in X. Okay. So before getting into the proof of that, I'm going to remind you of a lemma that goes into the proof of this. So let's suppose that U is a subset of X. Then U is open if and only if for every point of view there exists an open set, say nx, x has to lie in nx, and nx has to be open, as I said here, and nx has to be contained in U. And the point about this is just, of course, that then if you take all the nx's, that's a family of open sets, you take their union, it's not hard to check that that union is equal to U, and so that means that U has to be open because the union of any family of open sets is open. That was one of our basic axioms for topology. Okay, so we're going to use that lemma to prove the proposition. Okay. So we need to show that x plus y is open by the lemma so it's enough to produce for every point x that doesn't lie in y, an open set nx with x in nx and nx contained in x less y, which of course is equivalent to saying that nx intersect y has got to be empty. Okay, so now we have to somehow produce this nx. And remember, part of our assumptions for this proposition was that x is Hausdorff. So we're going to use the Hausdorff property now. Okay, so okay, so if you've got some, we fix the point x that's not in y, as I said down here, and then suppose you've got some point that is in y, well then obviously it's got to be different from x. So we can choose a Hausdorff separation. And of course the Hausdorff separation depends on what y is, so we're going to call it ay comma by. So that means that x lies in ay, y lies in by, ay and by open, and y lies in by. Okay, so there we go. So we've got these open sets ay and by. And now, of course, what the other assumption in the proposition was that y is compact. So that we have to use that somewhere. And how can we possibly use the assumption of compactness? We have to apply it to some open cover of y. But we've got an open cover of y now. I mean, these sets by, because y lies in by for every y. That means that y lies in one of the sets by. So we've got an open cover. So it means that we can choose some. Oh, actually, strictly speaking, it's not the sets. We have to think about the intersections. But so these intersections, they're open subsets of y, and so because y lies in y lies in by, so these guys are going to they're going to form a open cover of the compact space y. So we can choose some finite list with y being equal to the union of the sets just in that finite list. Which is equivalent to just saying that y is contained in the union of the b's. So now I'm going to let nx be the intersection of the corresponding a's. So this is the intersection of a finite list of open sets. It's a finite list of open sets, and remember, one of the axioms for topology, the intersection of any finite list of open sets is still open, and each of these contains x, so the intersection also contains x. Okay, but remember, nx was supposed to be disjoint from y, so that's the thing we need to check, that this nx is disjoint from y. Okay, so how do we check the intersection of nx and y? Okay, we want to prove that nx intersect y is empty, so for a contradiction we're going to suppose we've got some point in it. But remember, so y by assumption here, it lies in the capital Y, which was contained in the union of these by's. So y lies in byk for some k. So y doesn't lie in ayk because remember the a's and b's, they were Hausdorff separations. So yeah, we yeah. Oh yeah, I should have. The second condition that I should have made explicit here is that ay intersect by is empty. Okay. Yeah, so because of that, yeah, byk intersect ayk is empty. So and here we've got y is in byk, so y doesn't lie in ayk. Therefore, y doesn't lie in ay1. So that contradicts our assumption here that y was supposed to lie in nx. So we see that now that nx intersect y is empty as required. Okay, so now we've got our nx. It's an open set that contains x and is contained in the complement of y. We can do that for every possible x. So that proves that the complement of y is open, or in other words, y is closed, which is what we were claiming. So let's just finish by explaining quickly what we get by combining the last two results. So let's suppose that x is both compact and Hausdorff. As I said, these are very nice spaces that are both compact and Hausdorff. And y is a subset of x. And I claim y is closed if and only if it's compact. So the proof will suppose y is closed. We proved the first proposition in this video that closed subspaces of compact spaces are compact. So y is compact. And Suppose the Y is compact. Well, we know that compact spaces, compact subspaces of Hausdorff spaces are closed. That was the second of the two propositions we proved in this video. So Y is closed. Okay. So that's all we've got to say about compactness and subspaces.